We are discussing about activation functions and the loss induced by the activation function and the error gradient. Okay, and we chose sigmoid activation function as it is one of the most popular activation functions that are used in the network training. Okay, now let's spend some time in trying to understand the limitations of this particular activation function in the neural network training. Okay, these kind of limitations are easy to see because we already know that your sigmoid activation admits of a property. Okay, and so what happens is when you have an activation function and you are actually using it to minimize the error, right? I mean, minimize the error gradient, right? So you'd sort of imagine that some of the functional properties of this activation function could be responsible for faster convergence towards the gradient loss, right? I mean, and minimizing, finding the minima quickly, or maybe sometimes getting stuck in the local minima and so on. Correct? Okay, so what really happens is, I mean, if you do a critical point analysis of this guy, of this particular activation function, right? It is what I can say is that the critical points of this function is at, right? Which means, I mean, either the function has to be 0 or it has to be 1, right, in order to have a critical point, right? But then the other thing is, I mean, that the function itself is 1 over 1 plus e to the power minus x. So it has to be either 0 or 1 in order to have a critical point. Okay. All right. Now, can it be of any of the two values mentioned here? No. Okay. So, I mean, this guy will never be 0 and this guy will never be 1. So, that means the sigmoid activation has no critical point. So we don't know. I mean, there is no local minima, forget global minima. There is no local minima as well, which is why this sort of flattens out. I mean, if you look at the image, okay, if you recall the figure of the activation function, it flattens out at both tails, right? Let's look at the double derivative of this guy, okay, and see whether it has an inflection point or not. So if I do that, it's okay, and then naturally I know what this is. So this is sigma 1 minus well, I mean, this since it does not have a critical point, I mean, there is no point in investigating whether the second derivative is positive or negative, right, at the critical point, because the function does not have a critical point. So therefore, but I mean, can we figure out whether these have a point of inflection or not? I mean, the point of inflection are found by if d square and that's easy. So basically, I mean, you could have any of the three options, right? Well, the first two options are ruled out because cannot happen, right? So the only option that we have is this. So what does it mean? I mean, I know that. So therefore, so turns out it's pretty easy to solve, right? I mean, says e to the power minus x equal to 1, and then see the only possible value of, I mean, only way it would happen is e to the power x is equal to 0, right? Okay, so it's basically 0 comma 1/2 is a point of inflection. where, yeah, we can see that, right? I mean, if you think of the function itself, I mean, it's like this. So there is a 0, 1/2 is somewhere on the y-axis, and that's where the function starts flattening out. Okay, all right. So this is the reason why people try to explore other activation functions. Okay, all right. So let's look at the other activation functions now that we have noted that, so there is this, saddle problem, right? Okay, so let's see if this can be resolved or rectified in any other manner. So well, it's like structured in a similar manner. It's structured in a similar manner as to with a sigmoid function, but I mean, we do have more parameters to handle, okay, compared to the sigmoid function. Okay, all right. I mean, it's sort of more difficult from a practical point of view to make it work, but it comes with some nice analytical properties, which makes it a strong candidate for, producing pretty good accuracies. Okay, so this is what the function looks like, where your parameters are k and alpha, okay, where the k is assumed to be positive, okay, and alphas are restricted between 0 and 1. Okay, all right. Now the question is, can we sort of come up with expression for the gradient and from there show that whether this is profitable or whether there is some additional benefit of using this function. Okay, so let's do that. So what we can do is this function, because it looks kind of sort of ugly in the exponential form, we'll try to simplify this further. So it's like, I mean, if I do that, this is just ln of 1 minus ln of now we are sort of, I think we are prepared to do the derivative. So let's do that. And obviously there will be a chain rule involved here, and we have to do this carefully. So the first term inside the logarithm will have no bearing because it's a constant, and then we have to do these employ the product rule inside, right? So when you do that, it's like k and because of this minus here, this will become a minus. All right, I mean, I can pick this k and pull that out, right, and then sort of also see whether something additional, some additional simplification can be accomplished, right? So let's do that. So it's minus k over, okay. Now what can we do? Can we pull out x to the power alpha, right? I mean, and 1 minus x to the power 1 minus alpha? I think we can, right? Okay, so we will do that. So what we'll do is we pull out x to the power alpha and we pull out 1 minus x to the power 1 minus alpha. Now if you pull out x to the power alpha from the second term, no problem. From the first term there is x to the power alpha minus 1. So if you pull it out, you'll have alpha over x. Okay, and 1 minus x to the power 1 minus alpha, if you pull it out, it makes no difference to the first term. However, in the second term, what will happen is you'll have 1 minus alpha and you'll have 1 minus x. Okay, so far so good. Okay, now without touching the left hand side, I mean, I can just simplify this thing, right? I mean, just simplify this part. I mean, if I do that, it's like x times 1 minus x alpha times 1 minus x minus 1 minus alpha times x. So what I can see is alpha minus alpha x plus alpha x cancels out, and there is an alpha and there is a minus x, right? So it's alpha minus x with a minus sign in front. So I can just make this plus and rewrite this whole thing as x minus alpha. Okay, so in the next step, I'm intentionally changing a different color, using a different color. So it's like k x to the power alpha 1 minus x to the power 1 minus alpha over 1 plus kx to the power alpha 1 minus x to the power 1 minus alpha times alpha minus x over x times 1 minus x. Okay, well, it's kind of still looks sort of clumsy at this point of time, but then I think we can do certain simplifications. First of all, please notice that from this relationship, that 1 plus k x to the power alpha 1 minus x to the power 1 minus alpha is nothing but 1 over y, and therefore k x to the power alpha 1 minus x to the power 1 minus alpha can be simplified as 1 over y minus 1, which is 1 minus y over y. Okay, all right. And so therefore what I can do is I'll look at this, right? I mean, think about this. So this can be written as, this can be thought of as 1 over 1 plus blah blah blah, which is exactly y, correct? Okay, so this guy is exactly y, and this guy is nothing but 1 minus y over y, right? So let's do that. 1 minus y over y times y, right, times alpha minus x over x times 1 minus x. Okay, good. So now what will happen is, this y will cancel, and I can simplify this further, and I can come up with an expression for the derivative, which tells me that I have y times 1 minus y over x times 1 minus x times alpha minus x. This once again I get first order derivative of the activation function, which we can use in the gradient descent learning. Okay, but what's the difference between this derivative and the derivative of the sigmoid function that we observed? Well, there is a difference because first of all, a bunch of things that need to be noticed. Okay, that this guy has an exploding gradient problem. Okay, if x is equal to 0 and x is equal to 1. Okay, so we have to be careful about these two values. We have to be careful about x is equal to 0 and 1 values, because the gradient explodes. Okay, now but the nice thing is I have a critical point. Okay, so unlike the sigmoid activation function, the critical point is x is equal to alpha, and I mean that depends on the parameter alpha, right? I mean, so whichever parameter value I choose between 0 and 1, I could have a critical point. Okay, always. I mean, so therefore at least what I have is I can at least see whether the function is concave up or concave down, whether I could have a local minima or a global minima, and so on and so forth, right? At least, okay, because I have a critical point. Okay, all right, so let's move on. Let's move on with this, and probably we will see an activation. Okay, but I mean, I think I can probably show you the double derivative of this. Okay, so with this, I hope I can write this down, or clear this down. Okay, and I just copy this activation again, which is y times y minus 1 x times 1 minus x alpha minus x. Okay, now the idea is that what happens to the double derivative. Okay, it's actually a bit cumbersome to compute the double derivative, because it will, because of the expression, it will actually have a lot of calculations, in fact. And therefore I would like to skip that. But we can tell you, and I'll also show you from my slides, that the second derivative, okay, the second derivative is actually is a positive number. And this x is equal to alpha, remember, is a critical point. So what we are able to see is that at a critical point, we have a minima. Great. This is something sigmoid will never give me, correct? So you have a minima. So we have a minima, and therefore, I can hope that this nice theoretical property will actually help me achieve the gradient descent loss, right, or the gradient error loss, okay, much quickly, much more rapidly than sigmoid does. Okay, all right. So with this in mind, let's just move on to the neural network architecture, where I intend to show you the manner in which we use a neural network. Okay, and also I would also like to answer some of the other questions regarding the parameter tuning, right? Because remember, the activation function that we are claiming is this, correct? Where we do have to tune two parameters. Okay, so the question is, will the tuning effort? So the question is, will the tuning effort convergence guarantee? Okay, so that's the question. Will the tuning effort offset the convergence guarantee? Well, we can show, because in order to show this, I have to invoke something which is beyond the scope of the class. So I'm not going to, I'll just show you a few pictures, and just to convince you that the tuning effort is actually insignificant. Okay, if we explore some of the other functional properties of this particular specific activation function. Okay, all right. So let's now go to something that I wanted to talk about. Okay, all right. So so this is a more detailed exercise on the activation function. Okay, some of these things I'll just point out to the relevant areas. Okay, and remember what I told you was the second derivative. Computing the second derivative is really cumbersome. Okay, so therefore we skipped computing the second derivative, but I can show you very easily that and these are the contour plots of the function. So you can easily see from the contour plot, right, that when the value of k is fixed to 1, okay, all right, you can achieve a minima. Okay, all right, okay, all right. And then there is this thing known as a stable fixed point. As I said, I'm not going to talk about it, but as a promise to some guarantee of not spending enough time on tuning. We don't have to. So we can from this figure itself, we can figure out that for certain values of k, we have a stable fixed point, and we can achieve this flat minima. You can see that, right? These are the contour plots, and therefore we can easily use those k values and alpha values, okay, and in the gradient training. And that's exactly what we have done in the gradient training. When we trained, okay, we used these values, and that's it. We had to spend no time at all in updating these values, okay, because that would have been a nightmare. However, that's not what I intend to spend most time on. This is what I intend to tell you. I wanted to show you this second derivative, right? Okay, so let's look at this. Okay, let's look at this. This is the expression for the second derivative. I hope you can see this, right? Okay, you can easily see that when a critical point, which is at x is equal to alpha, so that means in the expression for the second derivative, when you plug in x is equal to alpha, some of these expressions will vanish. Okay, all right. And basically it comes down to a pretty simple expression, which is this. What do I see? What I see is, look, because the function is structured like a sigmoid function, the output y is between 0 and 1. Okay, and these are like sort of probabilities sampled from a probability mass function. These are not probability density functions per se, right? And x is restricted between 0 and 1. Okay, and therefore, I mean, you could, when you do that, typically what happens is when you do that, you are going to get this as a negative number. Okay, because the denominator is positive because x is between 0 and 1, but the numerator is positive as well, and so therefore the numerator the numerator is positive, the denominator is also positive, so the second derivative is positive. When the second derivative is positive, you ensure that there is a minima. This is exactly what we claimed, right? Okay. Now, all of these things I'll skip because these are not relevant to the course, right? I mean, but all it shows that the activation function itself can be linked to a binary logistic regression under uncertainty, but I mean that's not required. Okay, so what I wanted to show you is the following thing very quickly, is this, because we were actually talking about right, that how much time and effort we would have to spend in tuning. Actually nothing, right, because we have these parameters k and alpha, right, but these plots are sort of known as fixed return maps. So what will happen is, I mean, we have plotted this for multiple different k values, and we see that for all k values leading up to 0 and even beyond that, you would have this very random representation of the fixed point. So we really don't have a fixed point, right? Okay, and therefore, I mean, and this is true for a particular value of alpha and various values of k. Okay, all right. So what we know for sure is that for all negative values of k, we really don't have a fixed point, and therefore there is no point in using negative values of k when you tune the parameters, right? And then what we did was we fixed some alpha value and then plotted different values of k. Okay, and what we see is for values all the way up to 1, right? I mean, particularly from 0.9 to 0.95 and 0.98, where for different values of k we have actually a stable fixed point. So this actually tells us that, I mean, you keep your k values from 0.9 to 0.98, anything, right, and your alpha values in the neighborhood of 0.5, and you would actually get a pretty good accuracy. Okay, you really don't have to tune. And this particular Hessian representation also shows that the activation function not only has a local minima, it also has a global minima. Okay, all right. Now, what is interesting though, okay, this is really interesting, and I mean, I'm going to stop at this point of time, and when we come back we discuss more. In fact, what we do in the next lecture is to see the relation between the sigmoid activation and this particular activation that we introduced, okay, and whether other activation functions can be derived, other activation functions such as the rectified linear unit ReLU, whether that can be derived from the activation function that we just proposed, which is like sigmoid, the Saha-Bode activation function. Okay.